In this video, I'm going to be talking through how waves can be used with the Earth, essentially. So mainly talking about earthquakes. There's also two other types of sound that we need to talk about, and they're ultrasound and infrasound. Okay, I'm pretty much going to be using just a sheet. I'm going to quickly talk over the assessment points over here, because there's only really 2 or 3 sheets that actually refer to, so it's quite a small part of the course, although they like to ask about it on every single paper in quite a bit of detail, so make sure that you're aware of that. Okay, so in terms of these grades over here, human hearing range, okay, it's pretty straightforward. Okay, so the human hearing range is between 2 specific points. We can hear essentially between 20 Hertz, okay, and 20,000 Hertz. Now 20,000 Hertz can also be written as 20 kilohertz. Note that I'm doing a capital H and a small z. So that's the human hearing range. Below this, below 20 Hertz, we call that infrasound. Okay, infrasound is below 20,000 Hertz. That's the definition of infrasound. And above 20,000 Hertz is ultrasound. Above 20,000 Hertz is ultrasound. So that's greater than 20 kilohertz, and that is less than, less than 20 Hertz. Okay, so we need to state some of the uses of ultrasound and infrasound. I'll show you that in the document in a second. It does go through in that order. Then we need to talk about describing the Earth, and we need a diagram of the structure of the Earth. We need to talk about why it's difficult to predict earthquakes and the experiment for that. We need to explain what causes an earthquake and what causes the plates to move with some diagrams. And we need to talk about PLS waves going through the Earth and what that tells us about the structure of the Earth. Okay, so if we go to the pages on earthquakes on here, you'll see that it goes through that pretty much step by step. Okay, so here we go. Ultrasound, like I said, greater than 20,000 Hertz. Okay, and here are the uses. Sonar is the first one. There's an example of that below, where there's a boat, and the boat is sending out a wave. Sorry, it's gone too far. The boat is sending out a wave, and it's reflecting off a school of fish. It's coming back. Okay, and from that we can figure out how far away the fish are from the boat. Remember, the time is twice as long as it actually would take for it to get to there, because the wave goes there and back. So whatever distance you figure out, you need to half it. So that's what I go through in this calculation. Do read through that if you need to, because that is certainly a calculation that comes up at GCSE. So if you need to read through that, oops, is it right? You need to read through that. Let's just close that's right. You need to read through that. I'm going to leave that like that. Oops, easy again. Making that mistake. I'm going to correct my little mistake there. No, I'm not mistake there. If you need to read through that, read through this. Okay, pause the video, read through it, and it goes through the calculation step by step. Right. Other uses of ultrasound are communication between animals. In other words, dolphins do that. And also fetal scanning. Do not call it baby scanning or looking at babies. You can look at babies with your eyes. It's fetuses or fetal scanning is the idea of what we use ultrasound for. Remember, whenever there's a change in density, the wave bounces back. And that's what allows us, just like in this situation over here, the wave bouncing back, that's what allows us to see the baby, essentially, or to see the fetus. Okay, right, so that's the uses of ultrasound. Infrasound, okay, that's below 20 Hertz, that's what we were just saying before. It's below 20 Hertz, that's the lower limit of human hearing. That's how animals communicate. Okay, also you can hear animal movement in remote locations, so on the plains of Africa you can hear animals moving around using infrasound, and also volcanic eruptions and meteors. So when a meteor hits the ground or a volcanic eruption is taking place, infrasound waves are given out. Earthquakes sometimes give out infrasound as well. Alright, apologies for the beeping, that's just emails flying through to me. The next thing we need to talk about is seismic waves, in other words waves from earthquakes. This is the chunk of what what could be asked about here. Let me just make this go away. There we go, that's a bit neater. So, seismic waves are produced whenever there's an earthquake, okay? And earthquakes are caused by the movement of tectonic plates. This is the key bit. It's convection currents in the mantle, okay, in the mantle. Convection currents in the mantle that cause the plates to move. 2 marks there. Convection currents, 1 mark, in the mantle, 2nd mark. That is what causes the plates to move. You need to know convection currents in the mantle. Earthquakes are unpredictable, okay, but we have a good idea where they're going to take place, in other words, during plate boundaries, but they're unpredictable because we don't know what forces are actually required to cause them. Sometimes large forces are required, sometimes small forces are required. Okay, so we've got an experiment over here which shows the unpredictability of earthquakes. Okay, so you have sandpaper on a block, and the sandpaper stuck down so it can't, another piece of sandpaper stuck on a table so it can't move. So one piece of sandpaper on a table, stuck down, can't move. Sandpaper on a block, there's a bungee cord and a force meter, and you pull. And essentially different forces are required to make the block move. And that shows that earthquakes are unpredictable. In other words, a different number of masses are required to be attached on the end for it to move, which means that earthquakes are unpredictable. So when an earthquake happens, you have longitudinal P waves and transverse S waves. P waves are primary waves, they go faster, then S waves are secondary waves. When these waves reach a boundary, they are reflected. So when they reach a boundary, they reflect back. They can also change speed when they enter a different density, and we call that refraction. There's a gradual change in speed, means that they have a curved path. So they don't travel in straight lines through the Earth, they have a curved path. That means a gradual change in density. Okay? That's why that tells us about the structure of the Earth. Stat A, star knowledge. It tells us that there's a gradual change in density. Whenever there's a rapid change in density, they rapidly change direction. So you can see that over here. Rapid change in density over there. Let me zoom in on that. Okay, oops. Okay, so you can see that there's a rapid change in direction over here. You can see them changing direction quite quickly. Okay. Alright, so S waves only travel through solids and are slower than P waves. P waves can go through solids and liquids. They travel faster. Observing P and S waves has allowed us to determine the internal structure of the Earth. Okay, so P and S waves, and the fact that they refract more or less at certain points, okay, it means that we can actually determine the structure of the Earth. So technically, P waves should be getting to like over here and over here, but they don't, because of the fact they refract around that area. So there's a shadow. That's because when they come into here, they refract again, which means they miss this area. So that has told us about the structure of the Earth. So they've used that information to figure out the structure of the Earth. So here's some information about the structure of the Earth. Okay, so the Earth itself is made up of a solid crust. Apologies, let me just pull this down slightly. Oops, too far. Yep, so the earthquake is made of the Earth itself is made of a solid crust. It's about 20 kilometers thick. Then it has a liquid mantle. That's where the convection currents take place. Okay, and then there's a core of iron and nickel. That's what you need to know about the structure. Right. Sorry, let me just get a bit about seismometers up. Let me scroll through to it. There we go. Right, and the final bit you need to know about is seismometers. This bit's kind of tricky, so make sure you pay close attention to this. So seismometers detect these waves. They come out. There's the P waves and there's the S waves. And they can be used to determine the location of an earthquake. Because they travel at different speeds, we can figure out from the time difference how far away an earthquake was. So if you do that from 3 different locations, so this has been done from one location here. There's location number 1. This has been done from a second location here and a third location here. It could have been anywhere along that line, or anywhere along that line, or anywhere along that line. But where those 3 lines cross, we call this process triangulation because there's 3 points. Where those 3 lines cross, that's where the earthquake took place. So the earthquake took place there. Okay, that's everything you need to know about waves and the Earth.